Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Mechanisms for PFAS Contaminant Transportation. My name is Amanda. Firstly, in keeping with our custom, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. Before we get started, I'd like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, Geofabrics. Geofabrics is Australasia's geosynthesis specialist. They help their clients deliver and maintain their infrastructure by minimising risk and increasing value through the innovative use of geosynthetic products. For over 35 years, Geofabrics has supported the Australasian infrastructure sector on significant projects, from the Victorian level crossing removal to APLNG in Queensland and the Christchurch gondola in New Zealand. On these projects and every project they undertake, Geofabrics has a singular focus to provide smarter infrastructure solutions for their clients. Today we will hear from two speakers followed by a live audience Q&A session. And I encourage you to send questions through to our speakers via the YouTube chat box during today's presentation. I'd now like to welcome our first speaker for today, Associate Professor Will Gates. Will has worked with clay minerals and in particular bentonites and bentonite products. Since 2006, Will has focused much of his research on the performance attributes of bentonites used in geosynthetic clay liners. That research has led to bentonite specifications being adapted by the Victorian EPA 2010 Best Practice Environment Management Landfill Design Guidelines. More recently, Will has developed various instrumental methods to better probe the fundamental mechanisms of water clay behaviour, with the goal to better understand leachate barrier interactions. Will has been an active member of and has promoted Australian bentonites within both the US and Australian clay minerals societies. Please welcome Associate Professor Will Gates.
Thank you, Amanda, and thank you to Engineers Australia for providing this opportunity to speak about this very topical area. I hope to inform the audience a bit on the interactions of PFAS with minerals in landfill environments. PFAS have been manufactured and used since the 1940s. They are amongst the post-war wonder chemicals, and many aspects of modern society's creature comforts rely on PFAS. Since the 70s, PFAS have largely replaced chlorofluorohydrocarbons as refrigerants and in other critical products. As we're all aware, they have also been key ingredients in anti-film forming foams for suppressing and controlling petroleum fires. Lately, since the 90s anyway, the shorter carbon chain length forms have become more prevalent, and this is basically due to changes in production. Widespread production and use and the long-term environmental lifetimes of PFAS mean that PFAS can bioaccumulate and biomagnify. Legacy production of PFAS and its use remain key ongoing exposure sources. The properties of PFAS compounds, which have made them useful across a broad range of consumer and household products for many years, which include the carbon and fluoride bond strength, thermal and chemical stability, and surfactant properties of PFAS, also make them long-lasting, very mobile, and nearly ubiquitously present across terrestrial and aquatic, atmospheric, and anthropic ecosystems. These same properties also make them of concern for their toxicological impacts on the environment and on human health. Listed here are some of the more common PFAS compounds. Solubility is generally in the part per million to part per thousand range. pKa's are generally strongly acidic, meaning that most of the PFAS compounds are present in their anionic forms in most environments. The pKa is basically the pH at which the half of the PFAS compound is in its free acid form and half of it is in its anionic form at equilibrium. The critical micelle concentrations generally are higher than their environmental concentrations. Notable exceptions to that rule are PFOA and PFAS, which are all ingredients in AFFFs. The CMC is the concentration at which PFAS will partition into its own phase. And so this has a big impact on its ability to form films and as well as to be present in interfaces. In most cases, we can expect the PFAS to be highly mobile and ubiquitously present in its anionic form in most environments. Those environments preclude its adsorption and basically maximize its mobility. Shown here is a schematic on the interplay between the various ecosystems or the environments in which PFAS are known to have an impact. While regulation has reduced the direct source pollution of PFAS into the environment, considerable PFAS transfer still occurs via our built infrastructure, collectively called the anthrosphere or the anthropic environment. So as scientists, it's our duty or our task to ensure that landfills and other systems within our control are effective in minimizing the further transfer of PFAS into the terrestrial, aquatic, and atmospheric ecosystems. Modern consumer and household products are large contributors to PFAS in landfill. For example, in Victoria, upholstery and vehicle interiors are really important sources. Building and construction products, such as sealants and waterproofing, make up most wastes that contain higher amounts of PFAS. In the construction areas, concrete and bricks wastes are usually contaminated by PFAS and thus can become a source of PFAS in the landfills themselves. In Victoria, measured landfill leachates indicate that most PFASs are in the sub-part per billion concentration ranges. Also, in the operating landfills, most of the PFAS are in the shorter carbon chain length. And this is generally associated with being modern landfills operating now, utilizing wastes that have been produced since probably the 1990s. In this case, it's operating landfills accepting vehicle interiors. Notably, both of these landfills recirculated their leachate, which is an important part of controlling PFAS migration. The concentrations of PFAS that were observed in Victorian landfills hold generally true across Australia as well. These relatively recent findings compare the operating landfills with closed landfills and with different waste streams. The age of the landfill and whether or not it is operating are both highly relevant with regards to the potential for PFAS migration. And this basically reflects changes in PFAS production, use, and disposal in response to regulation. So going back to that table, we can see that if we compare the operating landfills on the left with the closed landfills on the right, we see much higher concentrations of nearly all PFAS compounds listed across the board. So we also can state that the wastes that come from construction and demolition remain a main source of PFAS in landfills. Returning back to that table, the center column, which shows the operating landfills accepting construction and demolition wastes, have much higher concentrations of PFASs than the operating landfills that accept the municipal solid wastes. Other important findings from these reports show that the associated chemistry of leachate is highly relevant for impacting PFAS migration. In other words, a high pH of leachate ensures that the ionic form of the PFAS dominates. If there's a high organic carbon loading in the leachate, either as in the form of dissolved organic matter or in particulate organic matter, then that will enhance the PFAS loading in the leachate. So that brief overview tells us a little bit of what we know about PFAS and wastes and in landfills in Australia. How do we now begin to control their fate and transport? How do we keep them from getting into the environment further from the landfills? In order to do that, we need to understand a bit more about their physical and chemical properties, such as their solubility, CMC and pKa, which we already have talked about, but also their equilibrium and stability and partitioning coefficients, and how these impact on their mobility at interfaces between phases and across these ecosystems. For compounds like PFOA and PFAS, whose critical micelle concentrations and water solubilities are on a par, a key parameter for their partitioning and migration in the environment is their ability to concentrate at the interfaces. These interfacial micelle and hemimicelle films concentrate the PFAS at the interface, which then drives concentration-dependent equilibrium processes such as diffusion, adsorption, desorption, and partitioning to all the various phases. So bringing this table back, which you've seen already, if it's apparent that both PFOA and PFAS have similar water solubilities and similar critical micelle concentrations. But the big differences exist in their pKa, the acid dissociation constant. The pKa of PFAS is such that we can expect in most environments that PFAS will be in the anionic form, whereas we can expect many environments in which both the anionic form and the free acid form of PFOA exist simultaneously. These differences are what drive many of the interactions between PFAS compounds such as PFOA and PFAS with mineral lining systems. And these mineral lining systems that we're going to now talk about include compacted clay liners and geosynthetic clay liners. So the main aspects of compacted clay liners that are important for their function are their mineralogy, their associated surface properties, their thickness, their density, their porosity, and their hydration status. The mineralogy and surface properties, such as surface area, surface charge, and surface acidity, impact how the PFAS itself will interact. For clay minerals with a permanent net negative layer charge, such as bentonites or the montmorillites within bentonites, the adsorption of PFAS is largely limited to the ionic bridging because they basically exist at concentrations below the CMC, but at pHs above the pKa. The minerals such as allophane that have a variable pH dependent charge, but have a high point of zero charge, that means that it has a pH at which the net variable charge is zero, is at a fairly high pH, then we can expect that direct ionic interactions of the anionic forms may occur because the surface charge is net positive and the PFAS is predominantly in its anionic form. So for example, allophane at pH of 6 would be net positive, but most PFAS compounds would be anionic. However, allophanes are very rare in Australia. Instead, Australians' soils are rich in kaolins, which while having variable charge, generally have a low 0 point of charge. So the pH is more like 4, at which they are net zero. So you have a greater chance for some PFAS compounds to be present in both the anionic and the free acid form when in contact with kaolins. Compacted clay liners should typically be a minimum of 600 millimeters thick, but the thickness only goes so far. Low saturated hydraulic conductivity is highly dependent on the compaction density and the low porosity that results from compaction, and thus that imparts a high degree of tortuosity on the liner system. Thus, the physical texture or the microstructure of the liner is very key to limiting the advective and diffusive transport of PFAS. In general, this will only serve to retard the migration of PFAS, but not stop it. From purely physical transport to limit PFAS to 30 years or so, a compacted clay liner must have a saturated hydraulic conductivity in the low 10 to the minus 9s or lower, or have a thickness approaching 5 meters thick. Now, I think you will all agree with me that a 5-meter thick compacted clay liner is pretty much impossible, certainly not economic to produce for a landfill. However, for a geosynthetic clay liner, typical saturated hydraulic conductivities are in the 10 to the minus 11 meters per second. And if we can achieve that, as well as having a 10 millimeter thick liner, then we can achieve a 30-year retention time in that liner. So a final important consideration for mineral systems is their hydration status. Saturated conditions tend to promote the presence of PFAS in the water column and preclude its presence in the interfaces, at least in the interfaces with the mineral phases. Unsaturated conditions do promote those interactions with the interfaces. So water mineral, air water, and air mineral interfaces will become important for PFAS partitioning. However, the jury's still out in terms of how that is actually interacting and controlling PFAS migration. So because organic carbon is present in many compacted clay liners in the form of natural soil humic materials, we can expect some interaction of the PFAS compounds with these. Soil organic carbon will have generally high cation and anion exchange capacities, have a large pH range at which these variable charges can occur, have high surface areas and associated porosities that are all responsible for PFAS adsorption and retardation interactions in compacted clay liners. The various forms of interactions of interplay result in ion bridging. So if there's a positive charged organic carbon, you can expect to see some ionic bridging, just as we saw for the positive mineral form. We also have direct electrostatic interactions. So that would be important in the case where the pH is above the pKa of the PFAS compound. In situations where the pH is not above the pKa of the molecule, then we can expect that other adsorptions such as phase partitioning interactions can take place. Covalent bonding, such as to directly to surfaces, appears to be fairly rarely observed for PFAS compounds. So to recap, the physical and chemical properties of mineral surfaces impact on the absorption and thus the fate and transport of the PFAS. If they're hydrophobic or poorly hydrophilic, or if they have a high surface area, we can expect that the distribution coefficient will go towards the mineral surface, and that will then result in retardation. If the pH of the solution or the leachate is such that it's below the 0 point charge of the mineral, then we can expect that the PFAS is going to be adsorbed if its pKa is low. If the pKa is high, then we can expect that adsorption onto the mineral surface will be lower. We can expect that the actual thickness of the liner itself is going to be very important for prolonging transport time, and this is just by virtue of the fact that we have a large amount of tortuosity. And that's very much also related to the density and lower porosity of the lining system. Wetter lining systems will result in probably a decrease in the partitioning to the mineral surface and an increase in the partitioning of the PFAS into the water column. Drier materials, we can expect the opposite, but the jury's still out because we don't really have enough information on that yet. The presence of organic carbon in the mineral systems is very important. And I guess basically a thick, high compacted, low porosity lining system with a high amount of variable charge minerals, including organic carbon, is going to be an ideal kind of a situation for PFAS adsorption. Geosynthetic clay liners, though, are different. In a geosynthetic clay liner, you have smectite or montmorillonite as the main mineral component of the bentonite. We don't expect them to have a large impact on the absorption and retardation of PFAS transport, certainly not much more than what we see for compacted clay liners. And our recent experiments basically show this to be the case. The difference, again, is that our geosynthetic clay liners have a much lower saturated hydraulic conductivity because we can manufacture them in such a way that we have low porosity, high density, and a high tortuosity. So what we found is with standard GCLs that we only have a minor retardation of PFAS. And part of this is because the tests are done under the saturated conditions. So if we actually conducted the tests under unsaturated conditions, we would expect to see a difference in the way PFAS is moving through the system. We don't have that information at this time yet. If we modify the GCLs with organic carbon additives, such as activated carbon, we do observe some retardation of the breakthrough for the longer chain PFASs. We see a drop in the first few pore volumes of flow. However, we see if we look at the total PFAS loading, it increases again. And largely that's associated with the shorter carbon chain PFAS molecules dominating the transport in the higher pore volume flow measurements. So basically, while the activated carbon GCL works well for the larger or longer carbon chain length PFAS, such as PFOA and PFAS, it's likely not so effective for shorter carbon chain lengths over time. And so this is going to be important for understanding when we design future landfills. I think it's really important at this point to point out that it's important to have landfill leachate collection systems associated with these types of lining systems. And that brings us to the modern composite liner systems, which would take into account multiple barrier systems and leachate collection systems. There's still a lot of information we don't know about how PFAS migrate in the modern composite lining systems. We have limited data on the efficacy of the various plastics associated with geomembranes, for example, in retaining PFAS. Most of the lining systems that have been developed did not have PFAS in mind when they were developed. They do seem to have, for example, HDP geomembranes do seem to have fairly good effectiveness. So we're at least lucky in that regard. I think it's really important to point out that the geosynthetic clay liners and compacted clay liners should only be considered as secondary or even tertiary lining components in the protection of the environment against PFAS from landfill leachates. Again, reiterate that leachate collection systems should be advised, and we strongly advise double composite liner systems where the primary geomembranes and subsequent geosynthetic clay liner systems work in tandem. And the leachates in the leachate collection systems should also be considered to be treated for removal or destruction of the PFAS. So you're basically over time reducing the load in that landfill. So I guess in conclusion, there are many knowledge gaps that are still associated with PFAS migration through mineral liner systems. What we do know is that we should not rely only on compacted clay liners and geosynthetic clay liners for their retention of PFASs. Again, the modern liner systems were not designed initially for PFAS specifically in mind, but our most advanced versions may prove highly effective. The efficacy of the hydraulic barrier systems in the components for containing PFASs are expected to improve with further research and development. Treatment of the leachate system should be considered, and given that the PFAS compounds have a long half-life, I think we should also consider destruction of the PFAS that's collected from the leachate collection, and rather than returning it back into the landfill itself. Thank you very much for your attention. I'm happy to answer any questions you may have.
Thank you, Will, for your insights. I'd now like to welcome our second speaker, Daniel Gibbs. Daniel is the General Manager of Technical Research and Innovation at the Geofabric Centre for Geosynthetic Research, Innovation and Development, commonly called GRID. The GRID provides solutions to engineering and environmental challenges through geotechnical review, empirical research, and product development. Daniel has over 17 years of quality management research, specification and method development, auditing, innovation, and analytical techniques in geosynthetics, with a specific focus on bentonite and geosynthetic clay liners. Daniel has authored or co-authored 11 research papers on geosynthetic performance and is an active member of various professional bodies, including ASTM committees D35 on geosynthetics and D18 on soil and rock, and the Australian chapter of the International Geosynthetic Society. Please welcome Daniel Gibbs.
Thanks very much, Amanda, and thanks also to Engineers Australia for providing me with the platform to talk about this subject. The title of my presentation today is The Development and Performance of a Hybrid Geosynthetic Clay Liner for the Attenuation of PFAS in Landfill Leachates. My name is Daniel Gibbs, and I'm the General Manager of Technical Research and Innovation at Geofabric's Centre for Geosynthetic Research, Innovation and Development, also known as the GRID. Okay, to start with, let's do a quick review of Per and Polyfluoroalkyl Substances, or PFAS. PFAS are a group of chemicals which are effectively made up of a fully or partially fluorinated carbon chain, or tail, and a functional head group. With the carbon-fluorine bond being one of the strongest in organic chemistry, some of the more salient properties of PFAS include being repellent to water and oil, and it also has some extreme thermal stability. Because of these, it has resulted in the development of a wide range of chemicals over the last 70 years, which have seen widespread application and have proven to be quite useful to us humans, such as non-stick cookware, fabric, furniture, and carpet stain protection applications, food packaging, some industrial processes, and at least historically in Australia, in some types of firefighting foams. Unfortunately, because we're constantly exposed to a wide range of chemicals in our everyday lives, and the fact that there are so many PFAS in existence, it makes large-scale epidemiological assessments on individual PFAS very challenging. What we do know is that generally, at least for the longer chain variants, which have been studied, such as PFOA, they're very persistent. They can bioaccumulate and biomagnify through the trophic web. They've been linked to the development of certain cancers and have been nominated as endocrine disruptor and immunosuppressant chemicals. Let's have a look at some of the ways that PFAS find their way into the environment. They can be directly released from manufacturing sites, of course, using fluorinated chemicals in their processing, in agricultural crops which have been irrigated with wastewater containing PFAS, aqueous film-forming foams, of course, and consumer products containing PFAS like carpets, food packaging, ski waxes, etc., as I mentioned earlier, which ultimately find their way into landfill. This is exactly the reason why we need to talk about PFAS in landfill leachate, with a specific focus on the performance of the lining materials used to inhibit the transport of these chemicals into the surrounding environment. Let's not forget the major exposure path for humans for these chemicals is ingestion, which includes consuming contaminated food or liquids, or simply breathing contaminated dust, which can accumulate inside our houses and offices, where we spend large amounts of time. So with all that incoming waste, which we saw in Will's presentation, we can see the necessity to generate some guidance around acceptable maximum limits for landfills, which we now have thanks to the development of the PFAS National Environmental Management Plan, or NEMP, currently in its second version, and this was created by the heads of EPA in Australia and New Zealand. The document gives practical guidance around the maximum acceptable levels of the three most studied long-chain PFAS, with different levels applied to the different types of lining systems employed by the landfill, with single composite lined landfills having a maximum leachable concentration of just 0.7 micrograms per litre in liquids, or a total concentration of 50 milligrams per kilogram in solids for PFOS and PFHXS individually or combined, and up to 5.6 micrograms per litre in liquids, or a total concentration of, again, 50 milligrams per kilogram in solids for PFOA. Now, obviously, the acceptance criteria can be applied to bulk loads of relatively uniform materials, such as excavated soils, prior to acceptance by a landfill. But when it comes to MSW waste or certain C&D waste, pre-acceptance testing is virtually impossible. So the only visibility we have on PFAS in these cases is to look at the levels in the leachate from the current waste stream. And this is helpful in providing some lining design guidance for the construction of future cells and also leachate ponds. Now, landfill leachate is a complex matrix of organic and inorganic chemicals which can make testing for these PFAS analytes a little more challenging than standard groundwater analysis. Still, there are a couple of standardized test methods which are employed, and these include direct injection or whole bottle extraction, and that's depending on the matrix. And both of these give us a reasonably accurate picture of the amounts of PFAS in these liquids. The levels of PFAS in landfill leachate, which Will presented, are generally supported by our own assessments here at the grid, where we saw higher levels of shorter chain PFAS, such as PFBA and PFBS, than their C8 counterparts, PFOA and PFOS, with a generally higher loading of carboxylic acids, represented here by the blue bars. It's interesting to note that all but one of these leachates had higher than the maximum allowable levels of PFOS and PFHXS allowed by the NEMP for single composite lined landfills, but they were generally within the range for double composite lined landfill systems, which, as we know, are a lot more expensive to build and CQA. Now, you may think, as a supplier of geosynthetic lining materials, for me, this may sound like an opportunity, but what if we could design a single composite lining system which would reduce the PFAS levels passing through the system to below the NEMP acceptance criteria for single composite lining systems by simply changing one aspect of the system? Before we get into that, though, there are a few key things we need to talk about to provide some context around lining design. Firstly, given that we know that there is PFAS in our landfill leachates and that it can concentrate with time, looking after these landfills long-term is critical, with most environmental authorities requiring at least 30 years of post-closure care. By this point, for well-designed modern landfills at least, there should be little to no leachate generation. The good news for landfill operators from a leachate collection and treatment point of view is that leachate generation has been shown to slow dramatically post-closure. And in this specific example of a landfill in Glades County, Florida, in the US, leachate generation dropped significantly within 2 years post-closure and then fell to virtually nothing after just 7 years. Obviously, this may not be the case for all landfills, but it certainly gives us some general insight into how long leachate may need to be managed post-closure. This is an important point to consider when discussing the hydraulic head potential and timeline of the required performance of basal liners, and in particular GCLs. Which brings us to the design of the lining system. In Australia, an accepted landfill liner and cap design include a single composite liner consisting of either a compacted clay or a geosynthetic clay liner, and this is overlain by a geomembrane. For critical applications, this system can also be doubled up. The improvement in hydraulic performance of a composite lining system over and above the individual components is well documented. But what about the transport of PFAS? There's been some recent work carried out by researchers here and overseas, which has shown that while PFAS can form micelles, as we saw in Will's talk, at higher concentrations and reasonably readily diffuse through the amorphous regions of polyethylene geomembranes, diffusion may be very low for the concentrations we find in a typical landfill setting. There's a body of work being undertaken at present here in Australia, which looks to quantify the effects of PFAS on lining materials such as HDPE geomembranes and GCLs. And this includes not just looking at how these chemicals move through the system from a hydraulic point of view, but also any detrimental effects such as stress cracking, which may occur over time with exposure to PFAS, because it's a surfactant. But based on our current body of knowledge, let's assume that PFAS quantities in landfill leachate are low enough to reduce diffusion through HDPE geomembranes to very low levels. That doesn't let us off the hook, though. What happens if the geomembrane has a defect or a hole? Then diffusive flux gives way to advective flux, and we now need to understand how liquids containing PFAS interact when in direct contact with the GCL components in terms of the impact on hydraulic performance and whether or not these chemicals are trapped in the bentonite, which has a history of being generally pretty good at trapping certain contaminants like heavy metals. We test the hydraulic performance of GCLs with deionized water to ASTM D5887 and the compatibility of many other solutions, including landfill leachates, with GCLs using ASTM D6766. These methods have specific set point values in terms of the confining and hydraulic head pressures, which interestingly were originally set with quality control in mind more so than around specific performance criteria in end-use applications. The pressures were selected to ensure the specimen could be confined and back pressure saturated using a hydraulic gradient that would produce a flow so that measurements could be made in a reasonable time period for QC and commercial labs. These specific pressures were reached by consensus at the time and only meant for comparing one GCL specimen to another based on the standard. As you can see by these examples given here, while the less than 5 or less than 3 by 10 to the negative 11 meters per second has now been embedded into industry specs for over 20 years based on a deionized water test, it's important to consider that actual hydraulic flux will change depending on the application and particular site conditions, including changes to overburden or confining stress, hydraulic head pressures, and the composition and concentration of the permeating liquid. So, for example, while the confining pressure may be similar in a landfill cap, if you have a relatively medium to low permeability soil in conjunction with a geocomposite drainage layer over the geomembrane and a mild slope, your hydraulic head potential is reduced to almost nothing. And your basal liners are likely to perform much better as well, given the much higher confinement and lower head pressure. A leachate pond is probably the closest you're going to get to these test values, but with more confinement, depending on the depth, but also a higher hydraulic head potential. Okay, let's take a look at the hydraulic performance. Here we can see the hydraulic conductivity of a standard GCL versus a polymer-modified GCL, both permeated with two different landfill leachates containing what I'd call reasonably typical or representative levels of PFAS as far as landfill leachates go. Leachate A gave final hydraulic conductivity values between 4.5 to 6 by 10 to the negative 11 meters per second for both GCL types, which is pretty good. And after around 9.5 months of permeation, leachate E returned values for both GCLs between 1 and 2 by 10 to the negative 11 meters per second, which is excellent. And these results are within the bounds of many of the Australian landfill leachates we've tested over the years. So hydraulically, at least, we see that the PFAS itself, and at least at these microgram and nanogram levels, don't appear to affect these GCLs in terms of their hydraulic performance. But what about their ability to trap PFAS? In some of our early research studies, we quickly discovered that the bentonite core, while it generally has a reputation for reducing contaminant transport due to its low permeability, it couldn't trap these three specific long-chain PFAS molecules very well in either standard or modified forms. Some of the uptake you see in these graphs, particularly for PFOA, could be linked to sorption onto the polypropylene synthetic components. We're investigating this further in a cooperative study with Monash Uni at the moment, so this could be included in a future webinar. So really the question is, how do you trap PFAS? Well, there's a range of products available that can do this, ion exchange resins and other types of polymers. A number of these have been successfully employed by water treatment plants for many years. One of them, which is activated carbon. Now, activated carbon is one of the most well-known and well-researched products available, with a proven potential to remove organic contaminants such as PFAS from liquids. It has a high affinity for hydrophobic compounds, which is why it works reasonably well to capture a range of PFAS given their hydrophobic tails. The extent of the adsorption is proportional to the specific surface area. So having an activated carbon with a very high specific surface area helps with total contaminant loading capacity and also the speed of uptake. As you can see in the photo here of these pre-fluid loss samples, which were mixed and aged, the activated carbon bentonite blend on the right was far more effective at stripping out a range of contaminants, including PFAS, from the leachate than the bentonite itself. Given the increased mobility of some of the shorter chain PFAS, one of the challenges with this product is that some activated carbons, at least, may not always effectively capture and hold onto some of these shorter chains to the same extent as the longer chain variants. So let's take a closer look at adsorption and how it works. Adsorption is the attachment of ions, atoms, molecules. These can be in liquid or gas form, and these attach to the solid surface of an adsorbent through weak electrostatic forces such as van der Waals. So it's a surface phenomenon as distinct from absorption, which is a bulk phenomenon where molecules are drawn within and become part of the absorbent material. It can be a physical bond called physisorption or a much stronger chemical bond called chemisorption. The large network of pores and the variety of pore sizes make activated carbon an excellent adsorbent. So now we know how effective activated carbon can be. How do we select the most appropriate type? Activated carbon can be made from pretty much any type of organic material, but ideally something with a high initial carbon content. Commercially, these are produced at scale from things like wood, coconut, and coal. You can also use waste materials such as apricot kernels and cherry pits. Different donor raw materials and to some extent different processing techniques result in different properties in the final product, such as specific surface area and porosity. Now, porosity for these products is categorized in terms of their differing sizes, from tiny micropores less than about 2 micron in diameter, through to mesopores, which are between 2 and 50 micron, and macropores above 50 micron. Activated carbon made from wood generally has a larger number of macropores, while coconut shell-based activated carbon has a higher level of micropores. Coal is somewhere in between these two with a reasonably balanced porosity, having similar levels of each pore size. And this is an important distinction in the context of having a product which has the correct size and number of pathways required to maximize PFAS adsorption. A further distinction is the type of coal used. Research by others has shown a higher PFAS attenuation capacity using bituminous coal over the younger lignite or older anthracite types. So we selected a particular bituminous coal-based activated carbon, which had already been designed by the manufacturer to assist in the capture of PFAS molecules. And we recently carried out a kinetics and adsorption isotherm study through ADE to understand and really quantify the performance of the activated carbon in isolation of the bentonite component. We used a landfill leachate as the contact liquid because it had a range of potentially fouling co-contaminants, which are a very important consideration when looking at performance. We looked at 2 different grades of the same product, one with a slightly lower overall surface area And the study involved things like reaction rates, equilibrium times using increasing amounts of activated carbon, desorption rates using pure water, etc. It's worth noting that the maximum addition rate of the activated carbon in this study was just 0.5 gram. So just summarizing the results, the removal order was PFHXS followed by PFOA, which you'd expect as there was less of these two longer chains in terms of their concentration in the original leachate. And we know that the longer chains are more readily trapped and are generally less mobile than the shorter chains. This was followed by PFBS and then PFBA, which also supports other research showing the higher mobility of PFBA and some other short-chain carboxylates over the sulfonates. The bulk of the sorption occurred within 24 hours, and that's common for a powder, which is far shorter than what you'd practically need in a landfill setting, but perhaps it's ideal for leachate ponds, which have immediate exposure. The short-chain absorption isotherms indicated multi-layer absorption or stacked adsorption, which can result in higher desorption levels or easier desorption under certain conditions. Long-chain desorption was lower or better than short chains. Both sorbents were very effective at trapping the long chains, but at low doses were less effective with the shorter chains. But still, even at 0.5 gram addition rate, even the more difficult PFBA achieved around 80% removal. Naturally, a change in solution chemistry may affect this for the better or worse, which is why targeted compatibility assessments are always recommended prior to product selection. So once we selected an activated carbon with the right properties and the right particle size, then we had to figure out how to manufacture with it. Prior to us spending around $1.5 million on upgrading the equipment, we ran several small laboratory trials and then larger scale online trials to qualify the product and the amount of activated carbon required to get that right balance between PFAS adsorption and GCL permeability using landfill leachates. So when it came to designing the equipment, we knew how much activated carbon we wanted to have per square meter, how we wanted to mix it, and whether we wanted a selection of other potential materials to be added as the body of research around PFAS transport and materials science grew, both in our lab and generally around the world. So we added 3 separate large hoppers for powders and also 2 special microdosing units for any polymers or other materials which we found to be effective in trapping long and short chain PFAS at low addition rates. We installed an automated sampling unit as well as a new core loading and rolling system. And this gave us a longer roll length capacity. And all of this really resulted in a great deal of future-proofed manufacturing and product design flexibility. The final result was a hybrid GCL product, which we named Saltseal. So if we now look at the long-term hydraulic performance over a few years, we can see a slight increase in permeability overall, but still in the 10 to the negative 11s. These particular Saltseal GCLs had a typical addition of around 1 kilo per square meter of activated carbon and between 4 to 4.5 kilos of dry bentonite. As I mentioned earlier, the PFAS in both leachates doesn't appear to have had a negative impact on the hydraulic performance. And I suppose going into this, we really wanted to preserve the permeability so that we remained within reasonable GCL leakage rates for design purposes. And we didn't want to disrupt the components of the GCL too much, such that we then need to rethink how we design with a completely new material or a certain aspect of the material. So we know Saltseal can retain good hydraulic performance over the long term in contact with landfill leachates, even with 1 kilo of activated carbon blended in, which is a non-swelling component. But how about the other critical aspects, the attenuation performance of PFAS over time? Well, that was excellent as well, especially given that, again, MSW landfill leachates are a chemical soup which contain a wide variety of co-contaminants alongside the PFAS. They're all competing for space on the surface of the activated carbon. The left-hand graph shows Saltseal's ability to strip the leachate of a range of PFAS, both long and short chain, while on the right we can see the performance of a standard unmodified Alkoseal GCL without any activated carbon. showing some attenuation performance, but not nearly as efficient as the Saltseal product. So if we just focus on the three main long-chain PFAS nominated in the NEMP, we can see that Saltseal is able to reduce the originally high levels of PFOS and PFH-XS, which were outside even the 7 micrograms per litre maximum for a double-line system, to just less than 0.03 micrograms per litre after 50 pore volumes of flow. Remember, this is permeated using actual leachate, and the conditions of the ASTM D6766 GCL permeability test method, representing 1.5 meters of simulated hydraulic head and a relatively low confining pressure. This means that in the landfill baseliner and cap, where pore volumes through the GCL are likely to pass through more slowly due to either increased confinement and or a lower hydraulic head potential, and the fact that leachate generation slows down dramatically post-closure, Saltseal may very well continue to provide attenuation of PFAS both during the operational phase and for many years post-closure, even beyond the moment leachate stops being generated. Naturally, this is dependent on the original PFAS concentrations in the leachate, the levels of co-contaminants, the other liner design elements such as the geomembrane and how well these products were installed and CQA'd, etc. But the data certainly proves that it can be done. And on the topic of CQA, let's take a look at the specification for Saltseal S1000 and S2000 GCLs. As I mentioned earlier, we purposely preserved most of the well-known properties of the Alkoseal GCL range in terms of the bentonite properties, the synthetic component masses, free swell, fluid loss, of course, remain in line with industry standards. We lifted the mass of the S2000 to a MARV of 4,000 grams per square meter. And that's in line with our research and the S1000 product. We've also slightly lifted the hydraulic conductivity to a MARV of less than 5 by 10 to the negative 11 meters per second based on the data we've collected to date on these products. This could change, but that's where it's sitting at the moment. Remember, that's a deionized water hydraulic value, not a leachate value, which could change depending on the constituents and concentration of the leachate. So that really leaves the main additions to the specification being around the activated carbon itself. So we've added 6 new tests here, which are largely MQC tests that are carried out on every batch of the activated carbon, which, depending on the addition rate inside the GCL, could cover several thousand square meters. So if you're specifying Saltseal, keep this in mind. One of the most well-known tests on activated carbon is called the Iodine Index, or the iodine number, which we'll look at in a little more detail in a minute. Other than that, the other properties are really there to tell a story about the origins and, to some extent, the quality of the activated carbon. For example, low ash, which is around 3 to 5, can indicate coconut shell activated carbon, but it's also indicative of acid-washed coal-based carbon. Coconut shell is harder, in the order of 98 to 99, and more dense than coal, ranging from 0.4 to around 0.54. So if you look at the combination of hardness, ash, and density, you can use this to determine the origin. So having a look at the iodine number is useful in quantifying the specific surface area or reactive potential of an activated carbon, in a similar way to how we use methylene blue titration to calculate the cation exchange capacity of the bentonite. There's a reasonably close relationship of the amount of iodine absorbed representing the total specific surface area. So for every milligram of absorbed iodine in the test, this roughly translates to 1 square meter for every gram of carbon. So the minimum iodine number for the activated carbon used in Saltseal is set at greater than 1,000 milligrams per gram, which translates to around 1,000 meters, square meters per gram. So we realized it was important to add a quantitative test for when it arrives on site to determine the amount of activated carbon inside the blended powder for CQA purposes. And that's where the percent carbon content test comes in. You can use either thermogravimetric analysis, or TGA, to quantify this, or you can use the quicker and cheaper, but by no means less precise, multiple furnace test. you only need a gram of the blended powder to run the test. So this can be easily extracted from the GCL samples sent to the independent lab for CQA analysis, assuming the lab has a muffle furnace, of course. The result from the test is then converted to the amount of added activated carbon and also by extension the amount of dry bentonite using the calibration curve, which was developed based on a series of TGA and muffle furnace tests that we carried out using pure bentonite, pure activated carbon, and different blend percentages of each material. Further to this, montmorillonite content analysis for the bentonite component via XRD has been embedded really in our industry for many years as a staple quantitative test. Now, you can either choose to have an independent lab collect bentonite directly from the sampling points online during production of the Saltseal, or you can send the blended powder from the GCL off to CSIRO and they'll test the powder as a whole and give you two results, an absolute abundance and a relative abundance. If you're simply interested in the montmorillonite content of the bentonite, then the value which is going to be reported will be the relative abundance value, as this will have had the activated carbon component subtracted. So that brings us to the end of the presentation. By way of summary, we saw that PFAS are ubiquitous in landfill leachates, largely due to the products which we buy, use, and that end up in landfill. We discussed the fact that the nominated pressures in the test methods for GCL hydraulic conductivity are largely used for QC testing. So the actual GCL flux may change depending on the application. We talked about activated carbon and the process of adsorption, which can be highly effective in trapping organics such as PFAS through hydrophobic interactions. We looked at the hydraulic performance of standard Alka-Seal GCLs with landfill leachates containing PFAS, showing minimal loss of hydraulic performance. We then explored the development of Saltseal and the ability to optimize the product for site-specific challenges using different raw materials. We saw that Saltseal can trap a wide range of PFAS in landfill leachates, which also contain a number of competing co-contaminants, over and above the standard Alka-Seal GCL, with only a minor impact on the hydraulic conductivity. And finally, we reviewed the new Saltseal specification, which lists a couple of the key raw material properties of the activated carbon, in addition to some of the methods which can be carried out by independent labs for CQA purposes. Other than that, thanks for your attendance. I hope you found the content valuable. If you'd like any further information about what you've seen here today, please reach out to me via email. Thanks.
Thank you. A big thank you to Associate Professor Will Gates and Daniel Gibbs. It's now your time to get involved, so please, if you do have questions, could you send them through to us via the YouTube chat box and just say who you're directing your question to, whether it be one of our speakers or both. Also, a big thank you to everyone who sent questions through on registration, and we might just start with those. So just starting with you, Dan, we've had a question that's come in from Jimmy, and Jimmy's in WA. Good afternoon, Jimmy, asking you, Dan, could you share with us successful projects with regard to the dewatering and management of PFAS contaminated groundwater? Thanks, Dan.
Thanks, Amanda, and thanks for the question, Jimmy. I think this is a very topical subject. I think more and more sites are being challenged with groundwater that's been contaminated with PFAS, and I think that that's just a natural progression as we move more into research. So, in terms of dewatering, there's a number of mobile services I know that are capable of going to site and treating that water. If you're looking at dewatering sludges that are contaminated with PFAS, then perhaps geotubes are an option. I know one of the polymers that we use is a cationic coagulant called polydadmac, which is successful with some sludges to dewater, but it also has some potential because it's a cation, has some potential to grab the anionic functional head of the PFAS. So if you've got sludges, then perhaps geotubes are an option, and we can model that here in the lab. It's not been done yet, so it would certainly be in the research space, but I think there's some validity there, and you can use polymers like polyamine as well, which are cationic coagulants. So Yeah, that's what I would suggest. But yeah, for the moment, in terms of sludges, geotubes potential there, but groundwater, I would sort of point you towards those mobile services.
Thanks, Dan. Will, do you want to comment on that as well?
No, I think that Dan covered it pretty well. Actually, I
Covered
think
it?
geotubes is a great solution.
So staying with you now, Will, we've had a question coming from Eamon, and Eamon's in the Northern Territory, asking you, does PFAS tend to adhere to the weathered materials? Thanks, Eamon.
Yeah, thanks for that question, Eamon. Rather than actually adhering to the materials per se, it depends on the material, of course. But for most materials that you'll find PFAS in, there actually adheres to the surfaces of the pores in the material. So for a great example is concrete. People wouldn't think that concrete is very porous, but it actually is quite porous. Um, Concretes that have been used for training grounds for aqueous film forming agents, for firefighting training, um, those actually can retain quite a large amount of PFAS. And when that rubble is then removed from those training grounds and put into landfill, it can then become a source of ongoing PFAS contamination within that new environment that it finds itself to. So really, it's because of the surfactant nature of the PFAS. The they really prefer to be in interfaces, and those interfaces include the pore surfaces. They include for example, a bubble, the film around a bubble, in say a foam. That's why they're used in firefighting, and in any kind of an interface between air and water and a mineral surface, for example, and then even between the mineral surface and the air, they will actually interact in those interfaces.
Thanks. Thank you, Will. And just staying with you there, we've had a great question that's come in from Albert. Good afternoon to you, asking, from this knowledge, what actions do you suggest should be done to reduce leaching PFAS? And what additional treatment of waste, increasing pH, work prior to landfilling and or new liner design? Well,
Yeah, well, that's a very challenging question, actually, and those are some of the questions that we're trying to address in all of our various researches. Um, so I guess probably the most important thing to realize with PFAS is that when you have a contaminated soil, for example, I mean, you dig that soil up and you move it to a new place, that is now putting it into a situation in which that PFAS is now going to rearrange itself into a new equilibrium condition. And so any kind of activity like that you do is going to promote the mobility of PFAS. So basically, to reduce its leaching further into the environment, then you need to put it into some sort of abundant and lined system, preferably something that is going to also have absorption capabilities, such as what Dan's talked about, and also leachate collection systems where we can collect that leachate and treat that leachate directly. So that's the main thing that I would say. Changing pH, I don't think is necessarily going to help. Most PFAS are in the anionic form above pHs of 4 or 5, which are normal in most soils throughout the world, and most waters throughout the world as well. So I think that the pH effect is probably going to be pretty negligible in terms of assisting that. And even if it was acidic and it was in the free acid form, it's not going to necessarily uh, hamper its mobility. It's actually could potentially enhance its mobility.
thanks, Will. And also, Albert asked, what the impact of a new liner design?
Well, of course, new liner designs would really be what's necessary. So, I mean, I think that some of our lining systems that we have currently, the best on the markets, are actually going to prove to be fairly effective for controlling and maintaining PFAS from getting into the environment, especially if they're operated continuously and managed properly and managed throughout their expected lifetime. So, for example, the study that I showed in my talk by Simpson that showed the 2 landfills from Victoria that had leachate collection system for the upholstery and automobile interior wastes. As long as those landfills are continuously operating and they're recirculating that leachate back into the landfill, that's going to stop that PFAS from further spreading into the environment. So I think that those are the sorts of things that the composite lining systems and double composite lining systems that incorporate the newest. They have the most flexibility for incorporating the newest kinds of findings that engineers are coming up with almost every day.
Thanks, Will. And over to you, Dan. Question coming from David. David's in Victoria asking you, what containment lifetime could be expected when the fluid is benign but is filled and emptied once or twice daily? For example, a pumped storage lagoon for energy storage. Thanks, David.
Thanks, Amanda. Thanks, David. That's also a pretty big question, to be honest. I think it comes down to, and when we look at containment, we really look at the system. So we take the performance of the individual components and we put them together, and that's just not the liner performance. That's looking at a range of things, which you're probably aware in terms of the geotechnical aspects, environmental considerations, like the type of soil, the preparation of subgrade, etc. The location of the groundwater table is really important. And if you look at the performance of the lining system, though, itself, I suppose assessment you'd look at the liquid in terms of the types, the concentration, how strong is that liquid? If it does have PFAS in it, then that's a consideration from advection, but also diffusive flux, as I mentioned. pH is really important as well. We know that PFAS are much worse in an alkaline environment and much more friendly for liner systems if they've got an acidic environment. But then there's the quality of the geomembrane, of course, the thickness of the geomembrane, how it's been installed, CQA'd, as I mentioned. So, and the maintenance, as Will said, maintenance of these structures are really important. But I think if you consider all of that and it's appropriately modelled, then you could expect, a good pond design with good CQA, with a relatively inert type liquid. A good estimate is about 20 years, I suppose, that you'd get out of an HDP single composite lined system. So, but yeah, it depends on the variables. UV is an important consideration as well. So,
thanks for that. And Will, over to you. We've had a question come in from Albert in WA asking, what insights can you share from observing the mass transport phenomena to the solution of reducing PFAS content in water? Thanks, Will.
Yeah, so this question is actually a very interesting one. I think it goes back to one of the first questions that was asked, is that basically because of mass transport is basically dependent upon the ability of that material to move in as a concentration dependent phenomena. Basically, you have to put it into a condition in which you're going to maintain and contain any of the leachate that comes from that. So again, reiterating, putting it into some kind of a bunded or lined engineered structure that can inhibit any flux of that system into the environment is what you really need to focus your attention on. Hope that answers the question.
Thank you, Will. And I'd just like to stay with you, Will, for the next question because it's come in from Samuel in Queensland asking you, what are the inexpensive remediation techniques available for water treatment, if any? Thanks, Will.
Yeah, I don't think there's currently any inexpensive remediation technique or treatment technique yet. There is certainly some effective treatment techniques, and these obviously include the activated carbons that Daniel's talked about quite effectively. There's also ion exchange resins, which are shown to work quite good in water treatment, for example, for groundwater. There's other methods available that allow you to concentrate the PFAS in different ways. So for example, if you have a fairly concentrated amount of PFAS in the water that allows that water to foam, then you can actually take advantage of that foaming and actually concentrate then the PFAS in your waste stream so you can pull that out. And that's been an effective way of remedying groundwaters and surface waters currently. And I think that was pretty much explored here in Australia more so than anywhere else. Hope that helps.
Thanks, Will. And Dan, we've had a question that's a great question that's come in from Takashi. Good afternoon to you. Asking, would you be able to comment on the regulatory framework of PFAS management for biosolids and their reuse and its economic impacts? Thanks, Dan.
Thanks, Amanda, and thanks, Takashi. Excuse me. When it comes to regulation, I think at the moment we've got, as I mentioned, the NEMP by the heads of EPA. And while biosolids don't have specific maximum limits nominated like they do for landfill liners, I think they do point towards the soil limits. So if you look at, I think there's the ecological direct exposure limit for PFOS is 1 milligram per kilogram for the soil, and PFOA is about 10 milligrams per kilogram. So that's in the NEMP. And then, of course, individual states in Australia, and I'm thinking about South Australia and in particular Queensland actually have. Queensland has the End of Waste Code Biosolids, which was published in January 2020. And that's got some guideline or trigger values for PFAS as well. Further to that, and I think a good summation probably, if you want more information and a nice, well-rounded answer to your question, if you have a look, earlier this year in March in the Water e-Journal, there was an article called or entitled PFAS in Biosolids, a review of international regulations. And it talks about it with regards to the Australian context. Now that's by H. Hall, D. Moody, and C. Vero. And it's a reasonably recent compilation of information about international regulations. So it looks at regulations around the world, but it also then focuses down into Australia. And I think in terms of regulation, it really is evolving as we learn more, as more research studies are done. Then we know which way we're going, and we've got the rest of the world as well to look to in terms of what they're doing and how they assess the use of biosolids. The economical impact will probably be there. How to quantify that's a really tricky one until that regulation moves forward. And it's the same for landfill lining design and leachate pond design and things like that. As the regulation could shift, from the three primary long chains that we're looking at the moment. And the reason why we're looking at those long chains is really it's because they're kind of a double threat set of products. They bioaccumulate in the body, but they also have very long half-lives in humans. So while they're in our body, they can be doing damage. And so I think there's that to consider. But as regulation moves forward, they could include a range of short chains, or it could be a total PFAS loading maximum that you're allowed. So, and depending on what those maximum levels are, will depend on the level of the economic impact.
Thank you for that. Thanks, Dan. Over to you, Will. And Takashi has asked another question and is actually thanking you for your presentation. So Takashi, thank you for that lovely feedback. The question is, Takashi would like to know more about PFAS destruction methods. Thanks, Will.
Yeah, thanks, Takashi. That's really nice of you. I didn't think I did that great of a job with my presentation, but that's nice. So destruction methods, there's several different methods for destruction of PFAS. Probably the most prevalent is pyrolysis. So it's a heat treatment, usually under a low oxygen environment, which then allows you to volatilize the PFAS into a gas stream that then gets put into a high temperature furnace, usually cooked off at about 1200 degrees or 1100 plus degrees Celsius, which then allows the carbon to fluoride bond to be broken. Now, there is one plant in Victoria that does do that, and they are certified by the Victorian EPA to actually treat AFFF and PFAS impacted soils and also PFAS laden waters. They currently operating pretty much continuously here in Victoria for the last 18 months or so for this procedure. There are other methods available that are becoming more and more commonly talked about. There's plasma, electrochemical destruction. These are still in kind of research stages, both in the U.S. and in Australia, as well as elsewhere. But they're showing some promise in being able to completely destroy PFAS. However, they can't handle the volumes that pyrolysis or incineration type methods can currently do. Does that help?
Thanks, Will. That's great. Moving on and staying with you, Will, and Dan, you might want to jump in, but we've had a question coming from Jonathan. Good afternoon. Quite a topical question talking about the Westgate Tunnel site in Victoria. The question, Will, is are you aware of the issues with PFAS material found at the Westgate Tunnel site in Victoria? And if so, can you comment on the disposal treatment? That's a big question.
Yeah, I think living in Melbourne, I think you'd have to have your head in the sand to not know about the PFAS problem with the Westgate tunnel soils. It is a serious issue in the sense that it's a large amount. I think it's on the order of 6 million tons of soil. I might not have that number correct, but it's quite a large amount. The levels of PFAS are very variable, as I understand. And the idea is to basically store the soil in landfills, and I'm not actually privy to what the landfills design and stuff will be. I think there's other people probably on this forum that are. However, there are some other methods that can be done to treat the soils, and one of the methods is, as I just described, is the pyrolysis system. So I'm involved in another project that's actually funded by the heads of EPA to look at the destruction of PFAS, and then in this case, what we're doing is actually looking at the reuse of the soil after this heat treatment because it's no longer suitable for soil. It's now an industrial waste. And are there any other properties that they're useful properties that the soil has that can be used for other things? So we've looked at it as a filler for replacement for fine fill in concrete. So the fine aggregates can be fully replaced if the soil's treated carefully and handled carefully afterwards. It does have some supplementary cementitious properties, so we can replace a portion of the cement in the concrete as well. So it brings you to being able to use this soil in a more effective way than to just straight put it into concrete. Into landfill. The issue is, however, is that it's a very large amount of material that needs to be moved around, and you have to question then how safely can you move it around to all the different places to be treated to then be used in this method. So it's still a long ways from actually making that happen.
Right, thank you for that. Dan, have you anything to add to that?
Look, obviously, as Will mentioned, we've heard about the Westgate Tunnel project. It's been kind of back and forth, to be honest. From a geosynthetic manufacturer's point of view, we're always ready to assist. If people are challenged and they want to know more or they want to know the interaction, then we're here and we have a specific niche laboratory which we can use to assess these materials, as you've seen. So outside of that, it's quite a it's quite a challenge, and it really has highlighted, I think, to everyone that PFAS can be very, very challenging to manage, and it can come out of somewhere which you wouldn't have even dreamed it would come out of. So, and lots of sites are continuing to have this issue, unfortunately. So, yeah, management, obviously, destruction. There's levels of of how to deal and manage with PFAS impacted materials. Landfilling's kind of down the bottom, as Will suggested. So, but yeah, if you absolutely need to, then you need to really look at all of this. If you're going to put it into landfill, then you're going to look at the lining system design and what the allowable amounts of PFAS are within the soil, and then how and the the leakage rates and all that sort of thing comes into it. So it's quite a process, to be honest, to go through all of that. And yeah, that's where I'll leave it.
Thank you for that. And coming to the close of our Q&A, this afternoon we've discussed the mechanisms for PFAS contaminant transportation. So I wanted to ask you both, putting a futuristic lens, what do you think are the key trends that we're going to see going forward in this field? And I'll start with you, Will, and then maybe finish with you, Dan. Thank you.
Sorry, Amanda, would you please repeat the question for me?
Yeah, I'm just asking, what do we see? We've talked this afternoon about mechanisms for PFAS, contaminant transportation. Obviously a complex field, very topical field. And over putting a futuristic lens on, what do you think are going to be the key trends going forward in the next few years, or the key areas of change or drivers of change?
Yeah, well, I think that really, as Dan has already mentioned, the regulations could really be the drivers here. As we get more and more information about PFAS and their impacts on ecosystems and human health, and how extensive they really are in the environment. I mean, pretty much everywhere that we've looked, we found them now. That's those are going to be the issues that are going to basically drive how we go. So I have a feeling that we're going to see total PFAS loading being the main issue that people are going to be looking at. Total fluoride levels, for example, and they'd probably have to qualify that as being total organic fluoride levels as being a measure that's going to be necessary to know. I think that probably as far as landfill lining systems go, the composite lining systems that we're all involved in here, I think that unfortunately we're going to have to be looking at more expensive and more extensive type of systems that are multi-component that allow for multiple avenues of interaction with the leachate in order to minimize the impact of this stuff over time. So it's going to become an engineering problem, but engineers can overcome most of these problems with a little bit of thought and mainly the mighty dollar. So just depends on where we want to put that dollar to.
Thanks. I guess, yeah, exactly. Thanks, Will. Dan, do you want to comment on that? Future trends, drivers of change?
Yeah, I completely agree with Will. Certainly, regulation is driven by the environmental impacts and the health impacts, obviously. Which, as I said in my talk, that it's really challenging to separate out the things that we're exposed to every day and the cumulative effect on our bodies. So, that regulation can only be driven by research into those areas. And to be honest, I don't think PFAS, I think it's going to be with us for quite a while. And I think people will still be able to manufacture with certain PFAS. I mean, if you look at things like the silicon wafer, which is used in semiconductor production, an absolutely critical part of our lives, our everyday lives. From mobile phones to cars and technology that just keeps on growing. So, they're really struggling to find something that's equivalent and has the same performance during that production process. So I think if that's the case, and we accept for sure that the PFAS are going to be with us, or fluorinated chemicals on some levels are going to be with us, it really comes down to the management of those, both in storage and production, but also how they're applied in the final product, and then where that final product finds its end. I think the future looks very good for us when it comes to the amount of people that are working on destructive technologies for those chemicals, separating them out. I mean, look, we've come so far when it comes to our understanding of chemistry and then sort of formulating and then deformulating things for useful purposes for humans. So I actually think it's going to take a little bit of time, but we'll certainly get there in the end. And we just have to find ways to live with these chemicals, as we have with many other things in our lives.
Thanks, Dan, and thanks, Will. And
Could I just add?
Yeah, of course, Will.
Sorry,
Please
Amanda.
do.
Could I just add? I think I just want to back up what Daniel just said. Is that if you look at the last 20 years of research that's been conducted on understanding the fate and behavior of PFAS, it's actually exponential, and it's probably I would expect that in the next 3 or 4 years that we're going to have even greater strides being made than what's happened in the last 10 years. It's just absolutely phenomenal how many people are getting on this, and some major experts from all fields of science and engineering are being involved in this. So I think, as Dan says, I think we're in a good shape for being able to solve this problem.
Thanks, Will. And thank you. It's great to finish on such a positive note. And it is all we have time for today. As always, the Q&A goes very quickly. And please join me once again in thanking Associate Professor Will Gates and Danielle Gibbs for their time and insights shared today. I'd also like to thank Engineers Australia's industry partner Geofabrics for making our webinar possible. As always, we're looking for your feedback on the program today to help us improve and plan for future sessions. So if you could please take a couple of minutes to complete the short survey in the description box below. Thank you again for joining us for this afternoon's Thought Leaders seminar. Look forward to seeing you again at our next webinar. Thank you and good afternoon.